Help you when I finish teaching, but that's going to be a little while. Hey guys, sorry about the delay there. Actually, I got a little stuck on the toilet. That coffee, you know how it does. Today we're going to continue talking about series. So I'm excited for you because today we're going to learn what are probably the most important convergence tests in terms of concepts. And those are called the comparison tests. And you'll notice some parallels with the comparison test for improper integrals. Namely, that there's a lot of inequality work and also that they're beautifully intuitive. So without further ado, let's get into this shit. Excuse me. This is strict. I just don't want to stop. So this is, as always, MAC2312. The section number is 004, which means this is a Calc 2 class. And the date today is October 20th, 2021. And today, we're going to talk about section of the comparison test. For series, which is section 11.4. So on Monday, we talked about the integral test. That was your second kind of convergence test for infinite series. Today, we're actually going to talk about two different tests. There's a direct comparison test, which is very much like your comparison test for improper integrals. And then there's another one called the limit comparison test, which is a little bit more powerful. Because it doesn't rely on inequalities. It relies on kind of an end behavior type thing. So yeah, that's it. I think these are so straightforward, especially the direct comparison test, so straightforward. I'd like to just dive right in. So let's do that. Let's do that. Theorem. And this theorem is called the direct comparison test. This says if 0 is less than or equal to an, is less than or equal to bn. So I have two sequences, an and bn. They're both positive, meaning all the terms in those sequences are positive. And term for term, the ANs are smaller than the BNs. Then sigma n from 1 or wherever to infinity Bn converges implies that sigma n from 1 or wherever to infinity of an converges. So sigma bn here is the series made up of the larger terms. So if the series with the larger terms comes out to be finite, then the series with the smaller terms must also be finite. This is like saying if you fit inside a finite box, you must yourself be finite. And if the series of the smaller terms diverges, then the series of the larger terms diverges. So if an infinitely large box fits inside of you, then you must also be infinitely large. That's the intuition. So if you're smaller than something finite, you got to be finite. Right? The ANs are smaller than the BNs, and the sum of the BNs is finite. So if you're smaller than something finite, then you must be finite. And also, if you're larger than something that is infinite, you must be infinite. When you use this test, sometimes you'll be thinking of your guy as the BNs, and sometimes you'll be thinking of your guy as the ANs. Don't get caught up with the labels, right? One of these will be your thing, and one of these will be something else that you come up with, right? One of these will be the terms from your given problem, and you'll either try to squeeze your guy underneath something that you think has a convergent sum, or you'll try to squeeze something underneath your guy that you think has a divergent sum. So kind of whether the series you're given is the ANs or the BNs depends on whether you think that series converges or diverges. Close the door here so I don't disturb my family. All right. So a nice simple example. Here's a series, and I'd like to know whether it converges or diverges. That's the sum from 1 to infinity of 1 over 2 to the n plus 1. So the plus 1 here is downstairs, but not in the power. Remember what I said. Whether you're going to think of our guy, in this case 1 over 2 to the n plus 1, as the AN or the BN, depends on whether you think your series converges or diverges. So you need to kind of have a guess in order to get started here. This series is very similar to another series. What is this almost the same as?
One over n.
Not quite like 1 over n, right? 2 to the n is very different from n itself. 2 to the n is very, very fast growing, whereas n is quite slow growing. So what is the kind of least significant part of these terms? Yeah, Richard got it in the chat there. It's the plus 1, right? Whether you've got 1 over 2 to the n or 1 over 2 to the n plus 1, those denominators those things are almost exactly the same. The only difference is this guy's denominator is a tiny bit bigger. Tiny bit bigger. So I would say, because 1 over 2 to the n plus 1 is very similar to 1 over 2 to the n, I think this series will do what? Converge or diverge? If you had sigma 1 over 2 to the n instead of 1 over 2 to the n plus 1, would that series converge or diverge? Well, don't scare me like this. Sigma 1 over 2 to the n, what kind of series would that be? You guys know this. I know you know this. Not a p-series. Remember, p-series is like 1 over n raised to a constant power. Would be geometric, right? Sigma, this thing, sigma 1 over 2 to the n, is that geometric series that we played with when we first started talking about geometric series. Here's our first example. I think this series will converge. So what I'm going to do here is use my direct comparison test If these things aren't popping into your brain right away, you need to be spending more time on the homework. We got to be keeping up with this stuff at this stage because it moves very fast. So I'm going to use my direct comparison test. I'm going to argue that this series is term for term. The terms of this series are smaller than the term of a series that I know is convergent. So here's what I would say. First off, 1 over 2 to the n plus 1, definitely positive, right? 2 to the n is always positive. You add 1 to a positive thing, it stays positive. You take the reciprocal of a positive thing, it stays positive. The terms of this series are like 1/5, and then 1/17, and then 1/33, and so on. All of the terms of this series are positive. And what's more, since this denominator is 1 bigger than 2 to the n, the whole fraction is smaller than 1 over 2 to the n. So here, this guy is like the an, this guy is like the bn. This is true certainly for all n greater than or equal to 1. Thus, since sigma n from 1 to infinity, 1 over 2 to the n is sigma n from 1 to infinity 1/2 to the n is a convergent geometric series R there is 1/2, so the absolute value of R is also 1/2, which is smaller than 1. It follows from the inequality and the direct comparison test that our series S equals sigma n from 1 to infinity 1 over 2 to the n plus 1 must also converge. So it's really not too bad, but there are some steps here where you need to make sure you're very, very comfortable. First and foremost, everything above direct comparison test. This sort of intuition is what sets us on the right path. And the thing that tells me, oh yeah, this is similar to this, is that their denominators are just off by 1. They're identical in every other way. And sigma 1 over 2 to the n, the series you get by making a series out of this sequence, is a geometric series. So we need to have this idea of when two things are similar. And we also need to be very comfortable with our bases for comparison. So the two main things that we're going to use for comparison are p-series and geometric series. Those are the series that we know the most about. They're the easiest to work with. You just look at them and you can say right away, that's convergent or that's divergent. The other thing that we need to be practicing for the direct comparison test, inequalities, right? Inequalities. Don't be shy. Just give me a react in Zoom. I'll give you a minute to get ready, find your reactions. Give me a react in Zoom if you understand why this inequality is true, if it's completely transparent to you. Okay, so we might want to talk just a little bit about inequalities because they are the nuts and bolts of the direct comparison test. I think I got a total of 5 reacts there. So first, this problem is done. All right, this problem is done. My series must converge because it is term for term smaller than this series, which is a convergent geometric series. All right. Where's this inequality coming from? Let's just take a second to talk about inequalities. So we're using them in a few different places, right? When it comes to your exam too, the places where you're going to need these inequalities are the comparison test for improper integrals, the squeeze theorem when talking about sequences, the direct comparison test here for series, and potentially the ratio test and root test. So let's just talk a little bit about inequalities. Some facts. If A is bigger than B, then 1 over A is going to be smaller than 1 over B. You can take reciprocals on both sides of an inequality, and the sense of the inequality flips over. So like 10 is bigger than 3, and 1/10 is smaller than 1/3. So if you have a smaller denominator overall, then the whole fraction is going to be bigger. All right, this is a very useful fact. And really, that's what we used there, right? So our inequality, we could have said, since 2 to the n plus 1 is bigger than 2 to the n, 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n. All right, that's where I got that inequality from. What other sort of inequality stuff do we want to talk about here? Here's another one. If A is greater than B, then A over C will be bigger than B over C. So if you have two fractions with the same denominator, and one of them has a larger numerator, then the one with the larger numerator is bigger, right? It's like 10 over pi is bigger than 4 over pi, because 10 is bigger than 4. I would say that these are the two main tools we're going to use for building inequalities related to the direct comparison test. All right, so a larger denominator means you're smaller overall. And if you have the same numerator, or sorry, if you have the same denominator, then a larger numerator makes you larger overall. So the example I said here, since the natural log of n is bigger than 1, the natural log of n over n is bigger than 1 over n. Now this is actually only true if n is bigger than e. So like when n is 1 or 2, this isn't true. But when n is 3, 4, 5, this is true. All right. Let me go ahead and show you a problem where we use this. So first off, what do we think is true about this series? What do you think this guy converges or diverges? Let's just work on building our intuition. Between the natural log of n and n itself, which one do you think is more significant? to the convergence. Yeah, the n itself, right? Natural log of n is very slow growing. N is faster growing than the natural log. It's still quite slow growing, but faster growing than the natural log. So here's my solution. Always tell your reader what you're doing. So we're running the direct comparison test. You could try running the test for divergence on this. But after one run of L'Hopital's rule, you'll see that the terms of the series do still go to 0. So this will sneak past the test for divergence. But based on our observation above, since the natural log of n is bigger than 1 for all n greater than or equal to 3, we have we have 0 is less than or equal to 1 over n is less than or equal to the natural log of n over n. Right, 1 over n is of course positive. This is true for all n greater than 0. And this inequality is true for all n greater than 3. So the whole inequality is true for all n greater than or equal to 3. So my terms, the terms of my series, are all larger than the terms of the series sigma 1 over n. We know sigma n from 3 to infinity of 1 over n does what? Does this series converge or diverge? Good, this diverges. It's a p-series, right? Remember, it doesn't matter where the series starts. It's a p-series. This thing inside is 1 over n to the 1. And 1 is not strictly greater than 1. Therefore, by our inequality, this inequality this guy, and the direct comparison test the series S equals sigma n from 3 to infinity natural log of n over n must also diverge. So if you're bigger than a divergent series, you're divergent. And if you're smaller than a convergent series, you're convergent. That's all the direct comparison test says. But you need to show that you're bigger than a divergent series. You can't just claim it. You need to show me the inequality. Right? Coming up with this inequality sometimes takes a little bit of work. Let me do one more direct comparison test problem. I'll yank it out of the book here. It's the classic. Also classic. Before we go to that, let's try something a little more fun. Okay. Something challenging. How's about Mhm. That's too similar to what we just did. Also a little too similar. Let's do number 6. Okay. So again, before we even get started, you want to take a look at this thing and kind of come up with a guess, because that guess is going to inform how you build your inequality. What's the most significant term in the numerator? Very good, n, right? Between the n and the -1, it's the n that really dominates. What's the most significant term in the denominator? Yeah, n cubed. So this thing is very similar to our series. S is similar to sigma n from 1 to infinity n over n cubed, which is sigma n from 1 to infinity 1 over n squared. So we think what? Since my series is quite similar to 1 over n squared, do we think my series converges or diverges? Right, because 1 over n squared is a convergent p-series. All right, so now I'm going to run the direct comparison test. And I'm going to try to show that my series is term for term smaller than 1 over n squared. First, n cubed plus 1 is definitely greater than n cubed, right? And that means that 1 over n cubed plus 1 is smaller than 1 over n cubed. Also, n minus 1 is smaller than n. So n minus 1 over n cubed plus 1 would be smaller than n over n cubed plus 1. And since 1 over n cubed plus 1 is smaller than 1 over n cubed, this would be smaller than n over n cubed, which is 1 over n squared. Putting this together, these give the inequality. Of course, this thing is positive again. N is running from 1 to infinity, so 0 is less than or equal to n minus 1 over n cubed plus 1 is less than, it is strictly less than, but we can say less than or equal to 1 over n squared. And this is true for all n greater than or equal to 1. Now we'll call this inequality star. So this is the inequality that I'm going to work with. we know that sigma n from 1 to infinity 1 over n squared is a convergent p-series. Why? Because here p is equal to 2, which is bigger than 1. Thus, by the inequality star, and the direct comparison test, our series S equals sigma n from 1 to infinity n minus 1 over n cubed plus 1 must also converge. That's it. Job done. So the fact that n minus 1 is smaller than n guarantees me that n minus 1 over n cubed plus 1 is smaller than n over n cubed plus 1. This is that second inequality fact. If you have the same denominator and a smaller numerator, then you are smaller overall. Then I use this fact. Since n cubed plus 1 is smaller than 1 over n cubed, this thing, right, the n over n cubed plus 1 must be smaller than n over n cubed because his denominator is bigger. So same numerator, bigger denominator will be smaller. Same denominator, smaller numerator will be smaller. The sort of inequality work you must get comfortable with. I promise it's not that hard. It's really just those two facts. But piecing them together is a skill that needs to be practiced. The other thing, we really need to know our p-series and we really need to know our geometric series. So we should be able to spot them quickly and immediately say whether they converge or diverge. Once we have this, it's just a matter of writing things down. But you do have to go through this process of writing things down because remember, these problems are all about the logic. Are there any questions on this problem? Okay. Sometimes you're given a series and you're able to do that thing where we say, oh, this is very similar to this other series, but you can't build the inequality. Either the inequality points the wrong way, or the inequality is just too hard to come up with. The classic example here . Actually, we could start this at 1 if we wanted, it doesn't matter. Yeah, let's start it at 1. 2 to the n minus 1. So just like our very first example, this series is almost geometric. If not for this pain in the ass minus 1, this would be a convergent geometric series. But it does have this pain in the ass minus 1. So first thing I would say here is that sigma n from 1 to infinity, 1 over 2 to the n minus 1 is very similar to sigma n from 1 to infinity, 1 over 2 to the n. So we think, we suspect of the series S converges, because it's super similar to this convergent geometric series. However, if you go trying to build the inequality, 2 to the n minus 1 is smaller than 2 to the n, which means 1 over 2 to the n minus 1 is bigger than 1 over 2 to the n. Now, the direct comparison test says if you're smaller than a convergent series, you must be convergent. If you are larger than a divergent series, you must be divergent. But what if you're larger than a convergent series? Like here, my terms are bigger than 1 over 2 to the n. Does that tell me anything? Yeah, this really doesn't help. All right, if you're smaller than a convergent series, you're convergent. If you're larger than a divergent series, you're divergent. But if you're larger than a convergent series, that shit could go either way. So we need a better tool. And that better tool is the other comparison test. So we're going to revisit this example in just a second. This other comparison test is called the limit comparison test. All right, and I'm going to try to explain to you a little bit where this limit comparison test comes from. I think seeing the proof of this will help you understand it because people generally struggle with it quite a bit. But first, let me just tell you what it says. This says if sigma an and sigma bn, and these could start wherever and go to infinity. I'll say again, just from 1 to infinity, but they could be from 0 to infinity or 10 to infinity, are both series with positive terms and L equals the limit as n goes to infinity of an over bn exists and is both positive and finite. Right? In other words, i.e. 0 is strictly less than L is strictly less than infinity. Then sigma n from wherever to infinity of an and sigma n from wherever to infinity of bn converge or diverge together. They do the same thing. That is what the limit comparison test says. And what I want to do is look a little bit at what this means. What does it mean to say that the limit of an over bn is some positive finite number? How does that connect these two series to one another? I want to be very clear that the limit comparison test does not tell you whether your series converges or diverges right away. It tells you whether two series do the same thing or not. So after running this test, you still need to tell me what the second series does. And then you can deduce that your series does the same thing. This is a place where people make a lot of mistakes. So please pay careful attention. before we get into this, before I actually use the test, I want to show you a little proof, because I think it'll help you understand why this test works. Suppose S equals sigma n from 1 to infinity of an, and that L equals lim n to infinity an over bn is positive and finite. Then for large values of n, what does it mean to say that the limit of the an over bn is equal to L? Well, it means that as n gets bigger and bigger and bigger, an over bn gets closer and closer to L. So for large values of n, an divided by bn must be really close to L, which means an is approximately equal to L times bn, where L is a finite positive number, not 0, not infinity, for large n. And this means that sigma n from somewhere, say capital N to infinity of n. So by large n, let's say for n greater than or equal to capital N. Then if I sum here from capital N to infinity, I get this is equal to sigma little n from capital N to infinity of L times bn, or approximately equal to, right? Because these are approximately, which would be the same as, since L is a constant, L times sigma n from capital N to infinity of bn. So when we say that the limit of the an over the bn is equal to L, what that means is that the tail of the series sigma an is very, very close to L, some finite number, times the tail of the series sigma bn. This is the tail of S, right? The late part of the series, which is the part of the series that determines whether the series converges, is very close to L times this piece, which is the tail of the series sigma bn. So if the series sigma bn converges, then his tail is finite, which means L times his tail is finite, which means the tail of S would be finite. So if sigma bn converges, then sigma an converges. And if the series sigma bn diverges, that means his tail is infinite, which means L, some finite number times his tail, would be infinite, which means the tail of S would be infinite. And therefore, if sigma bn diverges, sigma an diverges as well. All right, that's really it. Thus, if sigma n from 1 to infinity bn converges, its tail is finite. By the relation above, the tail of S would also be finite. So S would converge. also. Similarly, if sigma n from 1 or wherever Bn diverges, then its tail is infinite. So by the relation above, the tail of S would also be infinite. i.e., S diverges. So that's the big deal. If the limit of the an over the bn is a finite positive number, then the series sigma an and sigma bn have very similarly sized tails, right? The late terms in the series. In particular, if one of them is finite, the other is finite. If one of them is infinite, the other is infinite. So if the limit of the an over the bn is a positive and finite number, then the two series do the same thing. If one converges, the other converges. If one diverges, the other diverges. You're not responsible for this proof, but I think understanding this proof will help you understand how the limit comparison test works, and that will help you use it correctly. Okay, let's use it. So we had a problem that we were trying to solve. Let me return to that problem. I want to investigate the series sigma n from 1 to infinity, 1 over 2 to the n minus 1. And our observation that S is similar to the series sigma n from 1 to infinity, 1 over 2 to the n. So this is my an, this is my bn. With the limit comparison test, an is always your guy, and the bn is always the thing you're comparing to. So now I'm going to run the limit comparison test. And you should always tell your reader we're going to pick bn to be 1 over 2 to the n, or whatever it is you're going to pick for your bn. Make sure you state that clearly. Then L is the limit as n goes to infinity of an over bn, which is the limit as n goes to infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the n. Which is the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. You flip and multiply. And there's a number of ways you could take this limit. Both the top and the bottom are going to infinity. So you could use L'Hopital's rule. This is an indeterminate ratio. So by L'Hopital's rule, this is by L'Hopital's rule equal to the limit as n goes to infinity of, what is the derivative of 2 to the n? Does anybody remember how to differentiate exponentials that are not e to the x? Nobody? This is a Calc 1 thing. This is 2 to the n times the natural log of 2. In general, b to the n, or b to the x, would differentiate to b to the n times the natural log of b. This is a Calc 1 derivative. We should know this. So if I'm going to use L'Hopital's rule here, I need that derivative. So the top, his derivative is 2 to the n times the natural log of 2. Downstairs here, the -1 differentiates to 0. So he's also going to have derivative 2 to the n times the natural log of 2, and everything cancels. You get the limit as n goes to infinity of 1, which on a good day is 1. So L equals 1, which is positive and finite. So our series S and sigma n from 1 to infinity, 1 over 2 to the n, do the same thing. They converge or diverge together by the limit comparison test. But I'm not done yet. All I've shown so far is that my series does the same thing as sigma 1 over 2 to the n. So to finish the problem, you must come in here and say, moreover, sigma n from 1 to infinity, 1 over 2 to the n equals sigma n from 1 to infinity, 1/2 to the n is a convergent geometric series. Here, the absolute value of r is the absolute value of 1/2 is 1/2, which is less than 1. So the series S equals sigma n from 1 to infinity, 1 over 2 to the n minus 1 must also converge. That is how this test is used. So first you come up with a suitable series for comparison. Right? That was this step. We observed that our series is similar to sigma 1 over 2 to the n. Then you tell your reader, okay, I'm going to run the limit comparison test with bn equal to 1 over 2 to the n. What that means is you're going to calculate the limit n over bn. We call that number L. If this number comes out positive and finite, meaning bigger than 0, not equal to 0, bigger than 0, and also finite, less than infinity, then the two series do the same thing. Right? This series and sigma 1 over 2 to the n does the same thing. In our case, that limit came out to 1. So because that is positive and finite, the two series, my series, which I've just called S, so I don't have to keep writing it, and the series I'm comparing with, sigma 1 over 2 to the n, they do the same thing. They converge or diverge together. So if this is a divergent series, S diverges. If this is a convergent series, S converges. That's the end of the limit comparison test work. Limit comparison test says these two series do the same thing. In order to finish the problem and say whether S converges or diverges, I need to tell you what sigma Bn does. So we go on to say, moreover, the series I'm comparing with, sigma 1 over 2 to the n, is a geometric series, a convergent geometric series. Why is it convergent? Because the common ratio has absolute value less than 1. So my series and sigma 1 over 2 to the n do the same thing. Sigma 1 over 2 to the n is convergent. Therefore, my series must also be convergent. That is the logical flow. And you must use that logical flow every time you use the limit comparison test. You can use different words, but you have to convey the same thing. There is no part of this which we could omit and still have a complete solution. All right, any questions on this example? No, there's another way we could have calculated this limit. If you divide top and bottom by 2 to the n, then this would become 1 over 1 minus 1 over 2 to the n. And then that 1 over 2 to the n piece would go to 0. So we didn't need the L'Hopital's rule here. I just think it's the first thing most people would think of, so that's how I did it. But the other way to do this, we talked about back in 11.1, is to divide top and bottom by the fastest growing term. We call that our renormalization trick. So if you renormalize this limit, dividing top and bottom by 2 to the n, the top will become 1, and the bottom would become 1 minus 1 over 2 to the n. And that 1 over 2 to the n piece goes to 0, so you would get 1 over 1 minus 0, which is the same thing we got here, 1. L'Hopital's rule is, I'm honestly not a fan, right? I myself avoid L'Hopital's rule at all costs because it just, something about it just doesn't feel fully authentic. But I know that most of you probably prefer L'Hopital's rule to the algebraic approach, but whichever way you want to do it is fine with me. Yeah, generally to renormalize, you want to divide top and bottom by the fastest growing term that appears anywhere. So the fastest growing term here is 2 to the n, fastest growing term here is 2 to the n, so I would divide top and bottom by 2 to the n. If one of these was a 3 to the n, I would divide by that. Doesn't necessarily have to be the fastest growing term from the denominator, just the fastest growing term anywhere. If your goal is to keep the denominator finite, then you can divide by the fastest growing term in the denominator. Either one will work. There are some really fun problems that we can attack with the limit comparison test that are very, very hard otherwise. I'd like to show you one of those now. Before I show you this next problem, let me remind you of a special trig limit. Anybody remember this? It is 1. Yeah, this limit is 1. This is a special trig limit that you cook up at the beginning of Calc 1 because you need it to calculate the derivative of the sine function for the first time. So the first time you see this limit, you can't use L'Hopital's rule because you don't yet know the derivative of sine, and it's usually done with a geometric argument, looking at some areas inside a unit circle. But this is a fact, right? This is a fact. And a consequence of this is that if x is close to 0, then the sine of x is very close to x itself, right? Lim x to 0, sine x over x equals 1, means if x is close to 0, then sine x over x is close to 1, which means multiply both sides by x, sine x is very, very close to x. In other words, the linear approximation for the sine function near 0 is the line y equals x. All right, I want to tuck this in our pocket and investigate the series S equals sigma n from 1 to infinity sine of 1 over n squared. So building an inequality with this guy is going to be very hard. And I contend that it's not even obvious what's going on with this series. Like there's no immediate like observe, this is super similar to something else. It's kind of tricky. Unless you have this in your brain. Since sine x is very close to x itself for x's which are close to 0, sine of 1 over n squared is going to be very close to 1 over n squared for large n. All right, if n is very big, then 1 over n squared is close to 0. So the sine of that thing is very close to that thing itself. So we suspect that S is similar to the P series sigma n from 1 to infinity 1 over n squared. Like I said at the start, this is a problem that's very, very hard if you don't know what to do. That's why I'm showing it to you here. And the trick is this thing, right? This fact. Sine x is very close to x if x is a small number. So if I want to run the appropriate test here, you could try the test for divergence. It'll sneak by that because 1 over n squared goes to 0 and the sine of 0 is 0. If you try to run the integral test, good luck. First off, this is not a decreasing function. Secondly, the integral of sine of 1 over x squared is incredibly hard. You're not going to get it. I wouldn't be able to get it, not without power series. Third, you could try the limit comparison test. I'm sorry, you could try the direct comparison test, but there's no obvious inequality. The sine of some shit is not necessarily smaller than that shit. It's just close to that shit. Could be bigger, could be smaller. But based on this observation, we are inspired to use the limit comparison test with the choice Bn equals 1 over n squared. And then we're going to compute L as the limit n goes to infinity an over Bn. Here's a little bit of exam advice. when you start writing out a limit comparison test, write this piece first without the stuff plugged in. That way I know that you know what you're talking about, right? If that problem is graded out of 10 points, here's one of the points. Just write this and you'll get at least a bit of partial credit. Just some friendly advice. And that goes for all of the convergence tests, right? If you're thinking you might make a mistake or you're not 100% confident in the procedure itself, at least write out the statement of the test. So you show me that you know the theorem. And then if you make a mistake down the road, that's whatever, but at least I can give you credit for remembering the theorem. All right, an here is the sine of 1 over n squared. And bn here is 1 over n squared. Of course, you cannot cancel these. This 1 over n squared is inside the sine function for the same reason you cannot cancel the x's here, right? But we can calculate this limit. At a glance, what does this limit look like? What does 1 over n squared go to as n goes to infinity? Okay, 2 comments there in the chat. Let me deal with the first one first. So Daniel, it's true that the whole limit will be 1, but we asked what does 1 over n squared do? Yeah, so 1 over n squared goes to 0. So the top here is the sine of 0, and the bottom is just 0, which is 0 over 0, which is an indeterminate ratio. So I'm going to whip out some L'Hopital's rule here. The other question, I got something in a DM in the chat asking what does it say right after limit comparison test? It says pick bn equals 1 over n squared. So we're telling our reader what bn I'm going to use to compare. I'm going to compare my series with the series sigma 1 over n squared. And yeah, Daniel's correct. 1 over n squared goes to 0, and sine of 1 over n squared goes to the sine of 0, which is 0. So by L'Hopital's rule, and here we really do need L'Hopital's rule. By L'Hopital's rule, I have lim n to infinity. The derivative of the top is the cosine of 1 over n squared. And then by the chain rule, I need to multiply by the derivative of 1 over n squared. The derivative of 1 over n squared is negative 2 over n cubed. Right? I'm differentiating n to the negative 2. So that's negative 2 n to the negative 3. And then that same thing shows up down here. The derivative of 1 over n squared is negative 2 over n cubed. And I can cancel those. So I get lim n to infinity cosine of 1 over n squared, which is the cosine of 0. And the cosine of 0 is 1. Since L is, since L equals 1 is positive and finite, the two series S, my series, sigma n from 1 to infinity sine of 1 over n squared, and sigma n from 1 to infinity 1 over n squared converge or diverge together. That's what the limit comparison test tells me, that these two series, the one I was asked to figure out and the one I chose to compare with, converge or diverge together. Moreover, we know that sigma n from 1 to infinity 1 over n squared is a convergent P series. Here, P is equal to 2, which is bigger than 1. So it converges. Therefore, my series S equals sigma n from 1 to infinity sine of 1 over n squared must also converge. And I've said it a bunch, I will say it again, as you solve the homework problems, you need to practice writing this stuff out. I know it takes time. I know it leaves calluses. I know it's unpleasant and it wastes paper, but trust me, you need to do it. Right? If you don't practice the logic, you're going to be in trouble on the test. Questions about anything that's written here? All right, I think we are just about out of time. I posted a problem set for you guys earlier in the week that has, I believe, just some, what do we do? Does it have all the limit comparison stuff? I think it does. So yeah, you are now ready to finish up homework 9. The latter problems here are done by the limit comparison test. So I think at 23 is where your limit comparison stuff starts. Yeah. Yeah, and some of these are a lot of fun. Like this one is pretty cool. Do we have the other one? I think this one is very similar to the one we just did. 33 is kind of fun here. This is definitely a good limit comparison test. 36, you actually don't need the limit comparison test. You could do that other ways. There's one more problem I'd like you to work on. All right, it's not listed there. I couldn't find it in WebAssign, but it's a good problem. So before I let you go, let me just give you one more problem to work. What's this? I'm actually gonna have to look to remind myself. Is it in here? No, it must not be. Some pretty cool nth root stuff. Would be in here. Nope. No. Yeah, there it is. So here's a couple of fun ones for you to think about. These are both good problems. The second one especially is a good limit comparison test. The first one can be done several ways. The fastest way to do the first one involves a test that we haven't seen yet. So don't stress too much about this one, but I think you might enjoy working this one because coming up with your BN here, the thing to compare with, is actually very hard. It's not obvious. So to choose BN, think about the derivative of the ANs here, because as you've seen, we use a lot of L'Hopital's rule with this. The AN here is 2 to the 1 over n. minus 1, right? That's what the nth root is. So think about the derivative of that thing and see if you can come up with a good bn to compare with by thinking about that derivative. I will solve this one for you when we get to section 11.7. I'll also solve this one for you. But I think it would be good practice. And since it's not in the textbook, not in this section's homework on WebAssign, I just wanted to expose you to it now so you can start thinking about it. All righty, so that's the end of class for today. The test is neither Monday nor Wednesday of next week. So I know the syllabus has us taking the test a little bit sooner. We're just not quite there yet. So what sections do we have to cover before now in the test? We've covered 11.4. We need 11.5, 11.6, and 11.7 before we can do the test. So probably the test will be Monday after next. All right, I think this Friday, I want to work some problems and introduce you to the alternating series test. Next Monday, we're going to talk about absolute convergence. And then Wednesday, we'll probably need a little bit of Wednesday to talk about the rest of 11.6. And then 11.7, we will treat as like our study guide for test 2. So next Friday, my goal is to get to 11.7, and then you'll have your test on the following Monday. So the test is not going to be next Monday or Wednesday. It'll be the following Monday.
November 1st.
Is that the date? Let me see. That sounds plausible. Yeah. Yep. So your exam 2 is most likely going to be here. And I'll let you know for sure next week. I want to make sure that we're spending an appropriate amount of time on this stuff because this stuff is hard. Okay. After that, we're going to be talking about power series. This is the section that really kills people, 11.8, 11.9, 11.10. And you need to be rock solid on the first parts of chapter 11 to really get through this. So yeah, test 2, probably Monday after next. Then we'll move into power series. Once we get through power series, you're basically through the hard part of the class. So good news there. But the power series stuff is hard, and it's going to be on exam 3. Also on exam 3 will be all of the little application things that we haven't done yet. So there's a bunch of stuff with parametric and polar coordinates, surface areas, things like that, that rather than doing at the beginning of the class, I prefer to do at the end, because if they get squeezed, that's okay. The series stuff is the really important stuff. All right, so think hard about this problem. Please work hard on the homework. If you're struggling with anything, come talk to me. I've got an office hour today from 1 to 2. I'll have another office hour on Friday. That's it from me, gang. I got to get running. So I will see y'all on Friday.